So is it visible? Full screen? Okay. So again, good evening to all. Uh, the NPTEL course is Characterization of Polymers, Elastomers and Composite. This is week 9, already taught by Professor Santanu Chattopadhyay. And here myself, Samaresh Ghosh from IIT Roorkee as a TA for the doubt clearing session of this course. So we have discussed different analytical and characterization technique, and today we will discuss basically XRD, XPS and XRD. Now XRD, before going to XRD, first we'll discuss what are the different phenomena happen when an incident electron beam irradiated on a sample surface. So these are different phenomena like backscattered electron, cathode luminescence, auger electron, elastically scattered electron, and also unscattered transmitted beam. These are the different phenomena can happen. Now those actually depends on the atomic number and also the nature of the X-ray, whether it is hard X-ray or soft X-ray. So let's discuss one by one. So what is backscattered electron? So backscattered electron is nothing but just after uh, the irradiation, the electron will be in the opposite direction of the incident beam. It's almost close to the same direction, reflected back after the elastic collision with the sample or any material. And these backscatter electron nature will depend also on the nature of your sample, what is the atomic number of the sample, etc. Another type of phenomena that can happen is the emission of secondary electron. Now when secondary electron will came out, when the inelastic scattering is happen, that means it is not total energy of the incident beam is converted or transferred to the sample. After the inelastic collision, that is some amount of energy will be lost through heat or something else, and then that beam will ejects a weakly bound electron from your the sample, and that is usually ejects from the valence shell, because we know that since valence shell is far apart from the nucleus, so it is comparatively loosely bounded, and those electrons can be ejected. The third one is, this is also very important, that is the auger electron. Now when auger electron will eject, and what is the auger electron? So if let's say this is the nucleus, this is the first cell, this is the second cell, this is the third cell. Now there is electron, there is also electron in the second cell, and there is also. Now when incident beam is attack the nucleus and eject that electron, okay, now in this cell there is a vacancy is created. Now since it is the most closest one to the nucleus, so it cannot be remain as a whole, or there should not be any vacancy. In that case, another electron from the higher cell, it will come down, and when it will come down, the excess energy will be released. Now that excess energy can be applied in different physical phenomena. For example, that excess energy can be irradiated like X-ray, or that excess energy can eliminate another electron from the another cell. Now when that will happen, like an outer electron will be ejected, that is called the auger electron. So after creating the vacancy, an higher a electron from the others orbital will come down, and because of this come down, the excess energy will eject another electron from the another cell. That electron is the auger electron. The fourth one is the X-ray. So if that excess energy is released through X-ray, that is the that can also be happen, and this is the characteristic X-ray. So when an electron is coming down, that excess energy can be released also to the X-ray radiation. Unscattered electron, that is just it incident here, and without changing any angle, it will directly come out. So that is called the unscattered, and it is that process is the transmission. This is the transmitted electron. And elastically scattered electron also be released. That specific pattern gives information about the atomic arrangement in the space of a particular crystal. So these are the different phenomena can happen when a electronic beam is irradiated on a sample. Now what is X-ray? So we know there are different electromagnetic waves starting from radio wave to gamma rays. Now X-ray is a small part of the electromagnetic spectrum, and it is just below the gamma radiation. The wavelength is around 70 nanometer, and the useful range of the XRD or X-ray diffraction is 0.05 to 0.2 nanometer. So that will be our main interest for the XRD. Now how one can generate the X-ray? Because X-ray is a electromagnetic radiation and wavelength is 10 picometer to 10 nanometer, it can be produced by bombarding a very high speed electron on a heavy metal target. Now, a source of electron, it may be a tungsten filament, and a high accelerated voltage. There is also, this is cathode, there is also anode, and you are providing a very high voltage. When you are providing a very high voltage, that cathode will release the electron, and that electron will be targeted to a metal body. After that, the X-ray will generate from the targeted metal. And the anode is a tungsten rhenium on a monomerium core and baked with graphite or water core. So this is the total part, and after generating the X-ray, it will be come out through the beryllium window. So there are two different kind of X-ray. One is the Bremsstrahlung, and another is the, that is characteristic of the X-ray, when the interaction is sufficiently violent to ionize the targeted metal. So it will, as we know that because of that electron release, so there must be the positive charge will generate, and that's how it is ionized, and that electron removal must take place from the inner cell, and that's why you need a very high energy radiation. And there is two different X-ray, that is hard. For that you need copper or tungsten, those heavy metal, or soft X-ray can be generated from aluminum or magnesium, etc. So this is a schematic representation. You see, this is the copper anode, this is copper anode, this is the cathode, and you are providing a very high voltage, and in between there is a metal target, and from that metal, after bombarding with the electron, it will release the X-ray. And for that, you see the requirement of power is very high, around 2 kilowatt. Once again, so XRD is a non-destructive technique, you can say, and that provides detailed information about the structure, about the different phase of the crystalline material, and also so many other properties like crystallinity, amorphousness, obviously, and in essence, it, as there is also chance of formation of ionization, so in that essence you may say it is a destructive, but usually uh, we used to say that it is a non-destructive technique. And now what is the diffraction? So diffraction is the interference or bending of the waves around the corners or edges of any obstacle through the aperture into the region of geometrical shadow of the obstacle or aperture. So here what is happening? So this is the small aperture, and when through this edge it is coming out, it is formed these waves like this wave shadow, and when those waves are forming the interference, it will it is called a diffraction. So what actually happens in diffraction? First uh, reflection, and then followed by interference. This is the uh, main uh, phenomena how a diffraction can take place. So you must remind it that for diffraction it must be first reflection followed by interference. So crystalline materials are characterized, we know, with a periodicity of the arrangement in three-dimensional space of atoms. Now, parallel planes of atoms intersecting the unit cell are used to define the direction and distance of the crystals. So this is one plane. This total is the unit cell. Now, when these unit cells are combined together, it is formed a crystal. Now, in a unit cell, there are different planes. You know that Miller indices 110 or 100. These are the different Miller indices. Now, when the crystals are exposed to X-ray beam, X-ray scattered coherently by the regularly spaced atoms and producing a strong constructive interference of the emitted signal at a specific angle. And diffraction from different planes of atoms produces diffraction pattern. So there are so many different planes, and since those planes are arranged as a different uh, orientation, so it will form a diffraction pattern, and which contains information about the distance between the planes and obviously the arrangement of the atoms in a within a crystal. Now the angle between the incoming and outgoing beam direction is called the 2 theta. So this is the incident beam. 1 minute. So this is the incident beam, and these are the different atomic planes of a unit cell. Now after incident, there is a scattering is happening. Now the angle, this angle is the theta, and obviously this angle is also theta. Now the Bragg's law, that is n lambda is equal to 2d sin theta. N is the order, it may be 1 or 2 or 3, whatever. Now we can in order to constructive interference, the scatter beam must be in alignment. What is the difference in path length between A to A prime and B to B prime must be integral number of the wavelength. That's why n is always an integer value. Now this is table is showing there are 7 different types of unit cell. It is cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. And there are the difference among the 3 different axes and also 3 different angle. Now, what are the different parameters we characterize through XRD? Basically, wide angle XRD. So, wide angle XRD means the angle that we scan around 5 degree to 90 degree. Next, we will discuss about small angle. So, you just for this time being, for wide angle, as we are discussing right now, wide angle, the angle is around 5 to 90 degree. Now, what are the different parameters we characterized? First, obviously, the percent of crystallinity of any sample, that how much crystalline or crystallinity available, crystallite size, what is the size of a crystalline, and obviously the unit cell nature, whether it is cubic or rhombohedron. And another most important thing is distortion, that is also can be investigated through the XRD. And the long range order we can determine, and also the texture of any sample we can measure through XRD. Now, this is the anatomy of the XRD instrument. So there must be a XRD source from where X-ray will generate, and then there is a colorimeter through which it will be a straight single line, or we can reduce the width of the X-ray beam. And there is the sample and also goniometer. So what goniometer do actually, it changes the angle. Through the goniometer we can tune the angle, and after uh, irradiating with the sample, it will be reflected, and there must be a detector from which we will check the uh, we will get the data. Now, what are the different X-ray source used to generate the X-ray? So X-ray are produced in an evacuated X-ray tube containing a cathode, basically a tungsten filament, and a copper or molybdenum targeted metal anode operating at a very high voltage, around 60 kilovolt. The second component is the incident beam optics, that is collimator, to get a narrow beam, that I have already told you. After generating the X-ray, to uh, make it is a very intense single type of single line beam, we need the collimator, and that consists of two sets of closely backed metal plates separated by a small gap. And third important component is the monochromator. So usually whenever you are generating X-ray, now which electron is coming from the another orbital to uh, fill up the vacancy, based on that we can designate X-ray as a K alpha or K beta. So this K is the principal quantum number of a specific orbital. Now filter monochromator is what? X-ray beam will be partly monochromatized. Filter absorb considerable radiation and pass required radiation. So only if you are generating two different type of XR is generating, like K alpha K beta, you just need one K alpha. For that you need a monochromator. And it is made of a suitable crystalline material like NaCl or lithium fluoride or quartz, just to absorb the second radiation, that is K beta. The next is the goniometer. So the angles, what I have told, that usually 5 degree to 90 degree we maintain in wide angle XRD. Now angle between the source, detector and sample surface are set by the goniometer. For typically powder pattern, the data is collected to theta from 5 degree to 90 degree, and we can tune the theta in a different way. So for example, if the sample holder is fixed either horizontally or vertically, and the tube and detector only rotate. So if this sample holder, this is fixed, you can change the detector from in different direction to set the angle. In that case, we used to say it is a theta theta goniometers. Sometimes for a very small angle, to rotate a very small angle like less than uh, 1 degree, in that case sometimes you need to uh, also oscillate that sample holder in a different direction. In that case, both the sample holder and detector and uh, the X-ray tube you can rotate, and in that case we used to say as a theta to theta goniometer. The fourth component is, yes, 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 okay, yes. No, no, and that is the difference because for X-ray, now what is getting? There is visible light or UV light. Now that has different refractive index in air and glass. So that's why we use lens. Now here for X-ray it is same. So that's why you cannot uh, change the direction by the grating or any lens. That's why for X-ray we don't need any lens because it has the same for glass or whatever it is, it will remain same, and it is neutral. X-ray is neutral. It's not any charge particle, so it will not be reflected through changing the medium of the through which it will pass. So that's why we can change the angle of the sample holder or detector or the X-ray tube. Is it clear? Uh, I don't think that if you use any, it's not required to use any grating here. First of all, that's why we don't need any resin type of material also. And I don't know whether which kind of resin is used. I have to check also that. Since you are asking, so I'll check and I will discuss next week. Do you have any idea that what kind of resin they used? Okay, 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 okay. So next week we will discuss. I have also not that idea that whether resins is used or not. But what is the difference in between UVVs or any Raman like spectrophotometer with XRD? So here we don't use any lens. That is very important. Now, why we don't need any lens? That's why we need use this monochromator that actually separated out if they are generated like K alpha or K beta. So we cannot use two types of XRD, X-ray radiation. So to mute the K beta, we should have another chromator like LIF or NaCl or quartz. So that will uh, separate out the K beta. So only K alpha will go through the sample. Now why lens is not used here? Because we know for X-ray it will not change the reflection angle or refraction angle if the medium is different. Like for glass or air, it will remain the same. The fourth component is the attenuator. So that actually reduce the intensity of the X-ray beam that reaching to the detector. If very high intense X-ray is reached the detector, it will be saturated. So to reduce that, we required a attenuator. And last one is the detector. So that will converts the incoming X-ray to an electrical signal, and the unit is used usually counts per seconds. Yeah, counts per seconds. A detector are defined by their dimensionality and can be 0D or 1D or 2D. And working principle can also be vary with different detector. In common types includes the proportional counters, scintillation counters, and solid state detectors. From XRD, you will plot the intensity versus 2 theta. For wide angle, it will be around 5 degree to 90 degree. And depending on the diffraction angle, you will get different peak at different angle. Now, how quantitative analysis can be done through XRD? Now, diffraction peak position can be used to calculate the unit cell dimension. So, first you check a sample and then we use to match with a specific card number like JCPTS card number. Based on that, we have to calculate the D value. So, this is the equation from where you will get the unit cell dimension. Now, the convert the observed peak position 2 theta into D H scale. So, we know from the Bragg's law d equal to lambda by 2 sin theta, and determine the HKL of the diffraction peak from the JCPDS curve number, and then you can check what is the distance between two planes and also the unit cell dimension. We can also measure the crystallite size from the Device-Error law. So what is the size? Size is equal to 0.9 lambda by beta b cos theta, and where lambda is the wavelength of the incident X-ray. So for CUK alpha it is 1.54 angstrom, and B is the half maxima, full width half maxima. So if this is the peak of the X-ray, from the XRD we get this peak. Now B is the peak width at the half height. So this will be the B value, full width half maxima of a specific peak. From there we can measure the size of the crystallite. And what is the degree of crystallinity? So this is IC divided by IC plus IA. Now what is the IC and IA? Is the integral intensity of the crystalline zone and amorphous zone. Now what are the different application area? So first of all, to measure the sample purity, we can very accurately measure sample purity, because as it is interaction with the very close cell to the nucleus, so it is very inherent property of any material. And whenever there are different impurities present, we will get, for every element we will get the peak from the XRD. In that way one can check the purity of any sample. The second one is determination of the unit cell dimension, characterization of crystalline materials, and determine the structural properties, including different lattice parameters, if there is any strain or grain size, epitaxy, phase composition, and also orientation. Even if there is a presence of strain, you will get the peak position will at different, or peak shifting will take place, or d value will change. Characterize thin film samples and measure the thickness of the thin film can be done through the XRD. And also arrangement of atoms in a unit cell or in a crystalline material, the arrangement of atoms can be determined. Identification of fine-grained minerals such as clays. This is very much important for any composite. If someone is using clays in a polymer matrix, so first you check the XRD of the pristine clay, and after that if exfoliation takes place, so there must be the change in the D value. If during the processing of the composite the polymers penetrate in between the layers of clays, so there will be the change in the D value. So you can say that yes, exfoliation takes place after the reaction or after making the composite. And also determination of modal amounts of minerals can be done through XRD. Now in case of polymer, as we know that polymers are usually semi-crystalline type material, so there is a, it's not purely crystalline like any inorganic salt, and also the mechanism of crystallization in case of polymer is different. So it is showing polyethylene, we know that it is very much crystalline, around 90% crystallinity is there, and then polypropylene, that is semi-crystalline, cellulose, a biopolymer, it is also microcrystalline, and polycarbonate, we know this is transparent and amorphous and engineering plastic material. So you see the broadness of the peak is increased from polyethylene, which is much sharper, and to semi-crystalline there is also splitting, and also the broadness is increased. Now in case of polycarbonate, since it is transparent, the broadness is very much high, so crystallinity is very much low. Now here we will little bit discuss that how crystallization takes place. So there are different uh, mechanism, like back and fold mechanism, or there is also different laminar fibrils that form during the synthesis of the polymer and it will form the crystalline zone. So these area is the crystalline zone, and in between there is the amorphous zone. Now when there are also some zones where it's not perfectly oriented, but little bit there is a arrangement of the polymer chains, like 3-4 fibrils are there, and it is crystal nucleus, or sometimes it is called the psi molecule. So in that way, actually, polymer forms the crystalline polymers. So it is not like unit cell like in case of NaCl or any inorganic material. The mechanism of crystallization in polymer is little bit different, since it is a very it has very long chain, and it is entangled also. Now this is the small angle X-ray scattering, or SAXS. Now for wide angle we vary the 2 theta from 5 degree to 90 degree, but here the angle is below 5 degree or below 10 degree. So this is small angle scattering technique by which nanoscale density difference in a sample can be quantified. It determines the structure of particle system in terms of average particle size. So different uh, properties or different parameters we can analyze through SAXS. For example, if there is a nanomaterial and those are aggregated, whether it is a 4 particle aggregation or 10 particle aggregation, to know the internal structure of that aggregate, we can go for the SAXS. If the material is porous, we can go for the SAXS to determine that what is the how much porosity is there, and also some protein types molecule, what is the orientation of those long molecules, those can be analyzed through SAXS. What is the difference between SAXS and microscopy? So scattering pattern recorded and reconstructed in a mathematical way rather than optical way in case of SAXS. And also here lanes are not available, what I have already discussed, that why lanes are not available. And in the recording process, the phases of the detected waves are lost, therefore 3D representation of the object is not possible, and whole illuminated sample volume is investigated. As a result, the average value of the structural parameters are obtained. Now why it is like that? Because whenever, for example, this is the sample, this is the incident beam, and it will come like that way. So this total area actually it is measuring. Now since in case of microscopy we will discuss maybe in 10th week or 11th week, that we can focus as a very small zone, a pinpoint. So that's why we will get pinpoint data from the electron microscopy, but here we will get the average data of a small zone. And also that's why small details is not visible, and local structural details can be extracted from the small angle X-ray scattering. And in case of electron microscopy, that is also where the magnetic lens is used, further make it more intense to get more resolution, and small part of the object is magnified, average structures are hard to obtain. So we will get exact structure from the electron microscopy. We will discuss in later. Now we should here discuss about the basics of the SAXS. Now when a sample is illuminated by X-ray, it causes electron to oscillate at the same frequency. How actually it happen? For example, this is the nucleus, and this is the first cell, this is second cell. Now when an X-ray is irradiated, so it will takes different phenomena can happen, what I have already discussed the first slide. Now if there is a elastic pollution, there will be different phenomena. If it is inelastic, there may be different physical phenomena can happen. Now, another most important thing, that it may cause also oscillation of different electron at the same frequency. So whatever the frequency of the incident X-ray after radiation, it will cause the oscillation of others electron in the same frequency. Now when they are oscillated, so they may actually uh, then oscillation charge gives rise to coherent secondary electromagnetic wave with the same wavelength as that of incident beam. Like for example, if a music is going on, someone is dancing, so by looking that, others few also start dances and they actually uh, leave them left them, the first one. So in the similar way, after incident X-ray, it will generate the oscillation of others electron of the atom. Analysis of the scattered wave intensity as well as the angle of scatter, that is incident versus scattered X-ray, changes in polarization, wavelength and energy, and that can reveal the structure or elemental composition and atomic information about the sample. So in case of elastic, both the wavelength of the incident radiation and scattered radiation will be the same. Now why small angle? Now any scattering process is characterized by a reciprocity law which gives the inverse relationship with the object size. So whenever the angle is small, we can scan a larger object size. For example, here you see this is small particle size, object size. So this is the 2 theta value. Now when the object size is large, the theta value actually decreased. If you compare this 2 theta, the 2 has the smaller 2 theta value as object is proportional to the angle. Now SAXS actually measured the angles below 10 degree. It may go even 0.05 degree, and usually it performed in a transmission mode. Now wavelength of X-ray used in SAXS is 0.7 to 1.7 angstrom, typically 1.5 angstrom. Now if a wavelength much larger than 1.5 angstrom is used, photons would be strongly absorbed by the sample. So since as a quantum mechanically we can say it is a pact of photons. Any electromagnetic radiation is a pact of photons. So if the wavelength is much larger, more than 1.5 angstrom, photons will be strongly absorbed by the sample. On the other hand, if a much smaller wavelength is used, the scattering would concentrate at too small angle, making the practical analysis difficult. So that's why we should bound the angle around 1.5 angstrom, wavelength around 1.5 angstrom. Now SAXS provide information if the average radius of the molecule are about 5 to 500 times the wavelength used in the equipment. So that's why we can scan from 1 nanometer to 100 nanometer in SAXS, since the angle is below 5 degree or below 10 degree. Now what is the contrast of SAXS? Now the X-ray are scattered by electron within the sample. This means the more electron, the more scattering will happen. Meaning that if the elements or the sample is composed of a heavier elements, so heavier elements obviously has higher number of electrons, and that are highly suited for scattering experiment. So that's why to generate X-ray we need heavy metal like copper or tungsten, like that. Now contrast works based on difference in the electron density within the sample. A desirable sample would be highly electron dense and surrounded by a sparse medium so that there will be significant contrast and the sample can be easily analyzed. So it will be surrounded by a higher electron density so that the contrast will be higher. And yes, yes. Okay. So first of all, how X-ray actually generate, I have discussed in the first slide. For example, say this is the nucleus. There is first cell, second cell, third cell, like that. Now the X-ray generation depends that how much heavy metal it is. Now why heavy metal is required? Now obviously heavy metal means the uh, effective nuclear charge or number of protons will be higher in the nucleus. Now when a beam is incident and it eject this coarser electron, now there is a creation of vacancy is created when one electron is ejected from this cell. Now to fill that vacancy, another electron from this orbital will come out here. When this came here, so obviously that energy difference it must release. Now that energy release, that how it can release that energy, it depends on the nature of the atom. If this is heavy atom, so that energy will be higher and it will release as a X-ray. There is also another possibility. It may also eject another electron, that is called the agar electron. When if the excess energy is released through X-ray, that is the X-ray scattering. Now, if the atom is very much, I mean, for example, smaller atom or uh, uh, the atomic number is low, then excess energy will not released as a X-ray. For that, you need a higher or heavy metal atom. Is it okay? Now, the main thing is that it must have a higher effective or higher nuclear charge. Now, as the heavy atom, obviously, because of number of proton is higher in the nucleus, it must have the higher binding energy, na? Higher the number of proton, obviously, because of higher static interaction, it will have higher binding energy. So that higher the energy, there will be a higher chance to eject or to release the excess energy through X-ray. That's why we need heavy atom. And based on that also there are, for example, if the source is aluminum, it will generate the soft X-ray. It will not hard X-ray, since the atom is comparatively uh, less heavy as compared to copper or tungsten. So in case of if you are generating X-ray from aluminum magnesium, it is called the soft X-ray. In contrast, if you are generating X-ray from copper or tungsten, it is called the hard X-ray. So this is schematic diagram of a SAXS. This is X-ray tube and this is collimator to just make it is a single line beam, and here is the sample and this is the beam stopper and here is the detector. Now small angle versus wide angle X-ray scattering, the difference is the distance between the sample and detector is higher in case of SAXS. If you see the difference between the detector and sample, it is needed to be larger as compared to wide angle. Why? Because you see, if this is the very shallower angle it is irradiating, so to get it is a very small angle it is forming, so that's why you need a larger distance between the sample and detector, since the angle of incident is very much small. That is the main reason. So basically from SAXS you can also get data what you get from the wide angle X-ray scattering just by reducing the gap between the sample and detector. You can tune obviously the angle through goniometer, but just by reducing the detector and sample you can get the data similarly you are getting from the wide angle XRD. That is the beauty of the SAXS. Here it is much more prominent, you can understand. 1 minute. So this is the X-ray source This is the X-ray source. Here is the sample. And in case of wide angle, you see the distance is this much from here to here. But in case of SAXS, the distance is much larger. And that is obviously because of the incident angle is very small. And SAXS has a nanoscale resolution. And as we have also discussed that object size is inversely proportional to the angle. So it can cover 1 nanometer to 100 nanometer. Now, as in case of wide angle, the angle is more than 5 to 90. So we can only get resolution from 1 to 0.1 nanometer. So we can cover much larger area through SAXS. Due to this, SAXS can be typically used to analyze larger scale bulk microstructure within a sample, while wide angle X-ray scattering is more similar to X-ray diffraction and can observe atomic details. A small angle X-ray scattering and wide angle X-ray scattering can be done simultaneously and easy interchange, as it simply involves moving the detector, as I have told, closer to the sample. Now, what are the information is provided by small angle X-ray scattering? We can get the size of the sample or particle. We can also check the shape, whether it is cylindrical or spherical or palette, and also the surface through the porode uh, uh, position, where this cube is actually uh, the uh, 1 minute, the radius of the vector of the radius of gyration, this cube. So in case of surface, it is order of -4 or -3, but in case of size, it is -1 or -2. Yes, which one? This one? This one? 1 minute. Which one, please? Okay. So through SAXS, we can check different parameters of any sample. For example, what is the size? We know that size and shape are two different property, because when the different shapes particles are aggregated, it will take different size. Okay. Now, what actually measure here? This Q is the radius of gyration vector. Now, what is the radius of gyration? This is the distance between the center of gravity and the different, na, radius of gyration. What is the radius of gyration? If this is the, if this is the 1 minute. If, if this is the axis and this is the your material and it is moving, now obviously there are different atoms are oriented. Now, what is the center of gravity and the distance between these? This is the radius of gyration. Now, the Q is the vector of, because the vector of radius of gyration. So from here you will get better idea. This is Q. This is the Q. Now, for the shape and size, you see the order is different. For size, it is -1, -2, and for surface, that is the porode region or porode zone, it is in the order of this vector Q in the order of -3 and -4. Now, from the SAXS, by since it is a very small angle, and also we have discussed that it can cover from 1 nanometer to 100 nanometer, will get different data like size, shape, and surface of the same sample. Is it clear now? But from wide angle, since it is not covered more than, you see here it is covered only 1 to 0.1 nanometer. So that's why it is difficult to get everything from the wide angle scattering. But since in case of SAXS it is a small angle, and as it is a small angle, we can scan a wide or wide size or wide zone of a sample, that is 1 to 100 nanometer. And if we cover that zone, obviously I can get the data for what is the size or what is the shape and obviously the surface morphology. Now, application of SAXS in polymer, how what is the significance of SAXS in polymer? First of all, we can characterize a block copolymer from small angle X-ray scattering. If we plot the relative intensity versus Q, now a block polymer can exhibit multiple SAXS peaks since there is a different presence of different unit, repeating unit. So the periodic microdomain structure having a long range order, information on the microdomain morphology can be obtained from the relative position of this peak. They can exhibit specific spatial relationship depending on the shape of microdomain structure. For example, the ratio of the Q values at the scattering maximus would be 1, 2, 3, 4 for lamella. So it is predefined. If it is as lamella, the Q value, that is the vector Q, it should be 1, 2, 3, 4. If it is cylindrical or hexagonal array, it will be 1, root 3, root 4, root 7, etc. So you will get different peak position at different Q value. So this is the root 3, this is root 3, this is root 4, this is root 7. So if you are getting peak, you can check at what is the composition of the copolymer by looking at the SAXS data. Now you can also check at by providing temperature. So at the same time you are heating or cooling your material and you are checking the SAXS profile. Yeah. So based on heating or cooling, obviously the crystalline zone will behave differently and you can get different SAXS data from the instrument. For example, if you are heating from 39 degree to 177 degree, you see these peaks are reducing. The intensity of these peaks, if you check this one, when it is 39 and when it is 177, it is almost vanished. This peak is almost vanished, the root 3 one. So from there you can say what is the uh, microdomain structure if you heat the material after at a specific heat, how the microdomain structure changes. That can be possible from SAXS. The structure of polymer, whether it is aggregated form or not, and what is the shape, it can be identified. So that can be identified from the Q value. So the surface morphology or shape and size. Determination of the kinetics of the microphase separation and crystallization or melting of the constituent components in the block polymers. So just if you put the heat and you check the SAXS data, continuously monitor the SAXS profile, you can determine the kinetics of the microphase separation. And also the unique class of ion containing polymers or ionomers. So since there are presence of ions, obviously there will be the consist of cluster because of the interionic interaction, and that will of course form the crystalline zone. So these clusters usually have a dimension of in the range of 1 to 4 nanometer, and that can be characterized from the SAXS technique. The changes of mesomorphic structure of liquid crystalline polymer in solution in males can be characterized. So SAXS can be possible for powdery material, for solution material, or semi liquid or viscous type of material. You can check the SAXS. The next one is the X-ray photoelectron spectroscopy. Now what is the basics in XPS? So it is also known as the electron spectroscopy for chemical analysis. So we usually perform XPS to get the idea about the elemental composition. Now if a composite has 4 or 5 different elements, Now, what is the percentage of element? That also we can uh, check from the XPS data. So basically, it is a quantitative elemental composition analysis. Is so what actually done here is sample is irradiated with a monochromatic X-ray, for example, K alpha, and resulting in the emission of photoelectrons whose energies are characterized of the elements with the sampling volume. An XPS spectra is created by plotting the number of electron versus binding energy. Now, what actually happens? For example, say this is the nucleus and this is the first cell, this is second cell. Now, when X-rays is irradiated, now it obviously converts some energy. Now, these electron, yes, yes. For example, let's say you are preparing a block copolymer, right? Now, after synthesizing the block copolymer, you are cross-linking it through any cross-linker. Okay. Now, from XPS, first you check the block copolymer XPS data, and if it is cross-linked, if you check the XPS, obviously the binding energy of different, for example, C1s, it will change, or oxygen 1s, it will change. The binding will energy will not be same if it is actually interacting. So from there you can say certainly that yes, it is cross linking, or if there is any interaction, or for example, if someone is working on a metal complex, so first he should go or she should go for the ligand, check the XPS of the ligand. After adding the metal, if there is a complex formation, so the binding energy of the different element will change. So from there you can say how much what is the composition of your metals, or whether it is forming the complex or not. If it is not interacting, the binding energy will not change. That is very much important for XPS, and that's why it is uh, like NMR, we can assure whether something is happening or not chemically. That's why it is important. Now, why? Because binding energy for every atom, it is inherent property. It is inherent property. So it is fixed for each and different atom. Like if you consider the carbon 1s electron binding energy, so 1s electron binding energy for carbon, oxygen, nitrogen will be different. Now, if that oxygen is interacting with some other element, so then the binding energy of that specific 1s electron will be different if it is interacting. Why it will be different? Because obviously the effective nuclear charge will be different if it is interacting. So that's why the binding energy will change. Like similarly, what we check that in case of NMR, if there are electronegative atoms is surrounded, the delta value will be different. Similar, so here the binding energy of that electron will be different if it is interacting. Is it clear now that how we can get the composition from the XPS? And that's why it is very much authentic XPS data. Until unless it is chemically interacting, it will not change. You will not get difference in any binding energy value until and unless it is reacting or it is interacting. Now, yeah, yes, in case of UV, in case of UV also, if for example there is presence of oxygen and there is pi electron, so if that oxygen lone pair is engaged with other metal, it is or interacting with other element, So that N2 pi star will change. In the similar, so here also the binding energy will change. But FTR is not that much authentic. For example, if you mix A and B, so obviously you will get a different peak. You cannot assure 100% whether it is forming or chemical bond or covalent bond is forming or not. So what is the basic principle here? So the absorption of incident X-ray resulted in the ejection of the core electron. Okay. Now for every electron, we know that is bonded with the nucleus, there is a binding energy, and also there is another parameter that is called the work function. Okay. Now if H nu, that H nu, that is the energy of the irradiation X-ray, that will equal to phi, that is work function, plus binding energy plus kinetic energy. Kinetic energy means that ejected electron, ejected photoelectron, and that actually we measure what is the kinetic energy. Now since this work function and binding energy, these are constant for every atom or for each element, so only that kinetic energy will change depending on the H nu value. So for each element, the kinetic energy of the ejected photoelectron will change when the binding energy will different, because work function is fixed. It is fixed for any environment or for any case. So only binding energy if different, the kinetic energy will different. Now how the binding energy will be different? If the effective nuclear charge somehow changes, then obviously the binding energy will be different. So that's why we will get the XPS data and we can accurately say whether any changes occurring or not. Is it clear right now that why XPS is so much authentic and we can analyze the composition data? So when the electron leave the sample without interacting with the anything else and reach the spectrometer, the kinetic energy of the ejected electron is measured by the detector. So this kinetic energy actually measured through the detector. So each atom has a unique XPS spectra. Since the binding energy and work function is fixed at a same environment, but if the environment is different, then binding energy will be different, but work function will remain always same. And XPS is an analytic elemental analysis technique that is unique in providing chemical state information of the detected elements, such as distinguishing between sulfate and sulfide. Now since the oxidation state of sulfate and sulfide, if you check, the oxidation state of sulfur is different in sulfate and sulfide. Now since the oxidation state is different, so obviously the effective nuclear charge will be different for sulfate and sulfide, and hence the binding energy will be different. And if the binding energy is different, so at a specific wavelength, the kinetic energy will be different depending on the oxidation state. Depending on the oxidation state. That's why you will get very accurate data from the XPS. Yes. Okay. So, for example, 1 minute. If this is the nucleus, this is the first cell, this is second cell, this is the electron. So, for each electron, the binding energy means how much energy is required to eject it out from the nucleus to an infinite distance. So, it is fixed for each electron. Okay. Now, when I am irradiating with a radiation with energy H nu, this electron is ejected. Okay. Now for that, first of all, I must have H nu greater than the work function value. And I think you know the work function from the photoelectric effect. was done by the Einstein. Okay, so that at least that much minimum value is required. Now after that, we also need energy to overcome that binding energy that electrons specifically have with the nucleus. So when h nu is greater than the sum of work function plus binding energy, so it is better to make is a bracket, then the excess energy will be used as a kinetic energy. That had how much kinetic energy that ejected electron have after uh, ejecting from the atoms. So from the core shell, when it is ejected, that how much energy it has, because it is ejecting out na after collision with that H nu, it is ejected out from the cell. Now, obviously, we know that energy will be required as a kinetic energy, will be applied as a kinetic energy when it is ejecting. There must be some energy lost through the heat energy, but maximum energy will be converted to the kinetic energy after overcoming the work function and binding energy value. And that we are measuring that kinetic energy. Is it clear that what is the binding energy? For each electron at a specific, whether it is in a s orbital or p orbital, the binding energy is fixed. If it is a 1s, it has a specific binding energy. For example, if you consider the carbon 1s electron, it has binding energy around 285 electron volt. If it is oxygen, it will be around 530 or 540 something. So it is fixed for each and every element. Now, when binding energy will change, if the effective nuclear charge, because what is the binding energy? That is basically the electrostatic attraction, na? Because this is proton and this is electron. Now we know with increasing the oxidation state, the effective nuclear charge will increase, and obviously then binding energy will increase. Is it clear? If you have any doubt, please tell. Understood. Okay. Yeah. This one. Uh, this one. Uh, yes. FGK alpha. Okay. 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 1 minute. 1 minute. It is MGK alpha. So if this is your nucleus from here, okay, look here. So this is your nucleus, okay, and this is the first cell. So there is presence of two electrons. Let's say this is 1s. Now when X-ray is irradiating and it is ejecting this electron it is ejecting. So obviously now there is a vacancy, okay. Now for heavier atom, this first 1s orbital cannot be remain vacant. So there must be another electron which is just outside that 1s, let's say this one. Now it is coming here to fill up the vacancy. Now when that, so it is higher energy orbital. Now when it is coming here, say that excess energy, that is gap between this and this excess energy it will release, and that excess energy can be released through the X-ray scattering or through X-ray. So it will release that excess energy through X-ray. Now when this is happening just by uh, transferring of one electron from this first cell, then it is called the alpha. If that vacancy is filled up from the next cell. So just after one, if this one is coming down, this is called the beta. Like if the we used to say this is alpha carbon or beta carbon, the same concept is here, that from where the electron is coming. Is it just the side one, or just one one cell another, whether it is next to next or just next? Based on that, it is called alpha or beta. For example, if you have like C double bond O CH, so with respect to this C, it is alpha carbon, na? And this is beta carbon. Similar, so whether that electron transfer takes place from the next cell or next to next, based on that, it is called the K alpha or K beta. Is it clear that what is the difference between alpha and beta? Otherwise, I will discuss again. Okay. The same concept, whether it is alpha carbon or beta carbon. Similarly, whether it is a K alpha or K beta. Nah. You see, that's why K alpha proton with an energy 1253, and if aluminum K alpha, it is 1486. Now, why? Because aluminum has a it is heavier compared to magnesium. If you go copper, it is much heavier. So the kinetic energy will be equal to h nu minus binding energy minus work function, and obviously h is the Planck's constant. Now no photoemission takes place if h nu less than 5 or binding energy plus work function greater than h nu. So obviously the h nu must be greater than the sum of binding energy and work function. Then only it can eject the electron. So when that electron is ejected after overcoming the work function value and the binding energy, what is the kinetic energy? That actually we determine from the XPS. So photoemission process can be thought of 3 steps. First, photon absorption and ionization, then response of atom and creation of the photoelectron, and then transport of the electron to the surface. So this is initial state. After that, when that one electron is ejected out, it is become the plus one, since that electron is comes out from the atom. So this is the uh, final state when it is forming a positive charge. Now in XPS, we used to there are some different notation based on the quantum number. Now what is this? The you may say it is a one kind of term symbol. That is, n is the principal quantum number, L is the azimuthal quantum number, and J is the total angular momentum. This is L plus S. Now for n equal to 1, when principal quantum number is 1, we know L is 0, azimuthal quantum number is 0. And magnetic quantum number, obviously it has only two possibilities, plus half and minus half, and S will be half. If S is half, the XPS notation will be 1s. Okay. Now if n equal to 2, there L will be equal to 1. So that is basically p orbital. Now in case of that, there are two possibility, either L plus S, uh, m value is plus half and S will be either half or 3 by 2. How? If you check 1 plus half or 1 minus half. So if when L equal to 1 and you are taking magnetic spin minus half, that is L plus m. So 1 minus half equal to half and 1 plus half equal to 3 by 2. So there will be the two XPS notation, 2p half or 2p 3 by 2. In case of B, there will be also two possibility, 3d 3 by 2 or 3d 5 by 2, just by adding these two. So these are the different XPS notation of different electron, and we actually check the binding energy of this electron. So these are the you may say the identification number of a specific electron. Now the probability that a photoelectron will escape from the sample without losing energy. So actually what happens whenever it is irradiating, it is going at least few nanometer depth, and when from there the electron is coming out, there are different chance it may interact with other electrons, and based on that the mean free path length will be different. So for an electron of intensity I0 is emitted at a depth d. So for example, say from here that electron is ejected. So intensity I equal to I0 into exponential minus d by lambda cos theta, where lambda is the mean free path and theta is the photoemission angle. What is mean free path? Mean free path is before ejecting out from the atom, how much path it is traveling. And when d equal to lambda, so there will be the chance of 63.3% of electron will come out from the surface. If the depth is equal to 2 into lambda, so the chance will be much more. So with the increasing of the depth, the concentration or the intensity of the electron will be higher. That means more number of electron will come out. And here it is the binding energy. Once again, this is the characteristic of the core electron for each element. Since for each element the atomic number is fixed, so obviously the binding energy will be fixed for each core atom for each element. And the amount of energy required to separate an electron from the attraction force of the nucleus. So this is basically the electrostatic attraction force in between that nucleus and that specific electron. In case of gas, the binding energy can be represented as ionization energy. As we know, the amount of energy required to remove one electron from the first cell to infinite distance, that is called the ionization energy, and it follows the energy level as 1s, binding energy of 1s greater than 2s greater than 2p, and you absolutely know that from your 11th or 12th standard that why 1s electron has higher binding energy. Since it is much more closer to the electron, the nucleus, obviously it has a higher binding energy. And binding energy of orbital increases with z, so this is the effective nuclear charge. So that's why Na1s less than Mg1s less than aluminum 1s. And this is schematic of XPS. So here you are generating that X-ray, that is K alpha. This is your monochromator, this is the sample, and after interacting it will release the photoelectron and it will travel through this tube, and here you should provide a voltage to synchronize it, and after that there is a detector to check the binding energy, that how. So obviously if there are different elements, the ejected electron will have different binding energy. So for each and every element, since the binding energy will be different, you can get that what are the different elements present and how much percentage is present. So this is a schematic diagram of a XPS peak analysis, and it's usually the binding energy scale 0 electron volt to 1000 electron volt, and the most intense peaks are usually the photoelectron peaks. So there are also different electrons or different physical phenomena can happen, like Auger electron ejection can take place, or there are extra satellite electron, or sometimes some valence band electron can ejected from valence band, and obviously since valence band are the far apart from the nucleus, it must have a very low energy around 20 electron volt or 10 electron volt. So everything you will get, but you have to fit. So what we used to do after getting the XPS data, we have to fit it what we need actually. Based on that, we have to fit it through different software, expert, or there are different software available. So background comes from electron excited by the X-ray bounced from radiation at the low binding energy, and from inelastic scattered photoelectron at higher binding energy. So there are different possibility of uh, different ejection of different electron, whether it is from the valence band or from it is agar electron. So everything you will get, and obviously they must have different energy, and that's why you are getting a different position and different intensity also. So there is also one important term is the Shake-up peak or loss peaks, that is resulted from the de-excitation process. So what happen when one electron is ejecting out? So when it is coming out from the bulk or from a certain depth to surface, and it is interacting with valence electron, and that can excite the valence electron also to a high energy level. So the core electron kinetic energy is reduced by interacting with the valence electron to some quantized amount, and the result is a peak which occurs at a few electron volts and higher binding energy than the core level XPS peak. So Shake-up peaks are similar to Shake-up peaks, but instead of exciting an electron to a higher rate, the electron is ejected from the atom. So these are the very small intense peak. This is the Shake-up peak. These are the Shake-up peak. So when an electron from the a specific depth, it is coming out to surface, then it is interacting with the valence electron, and that way it is increasing the or it can excites that electron to a higher binding energy. There is also an extended tail may appear, and also plasmon loss. It arises when an outgoing electron excited a collective oscillation in the conduction band also. It's not only valence band, it may also interact with the conduction band, and that is called the plasmon line. So these are the, so you will also get with a specific silicon 2s or silicon 2p, there are small lines. These are called the plasmon lines. So that's why we need to do peak fitting, and peak fitting it is required to determine if the multiple chemical states are present and to determine the relative concentration of each component. So if since there is three, you see there are three different carbon. So it is C double bond O, this carbon, it is also C double bond O and single O, and this carbon is not bonded with any electronegative oxygen atom. So based on that, the peak position you see are different. This is the A, that is only C double bond C. This is B, that is CH2, and this is C. Now why? As the electronegative atom is directly bonded, so the effective nuclear charge that first 1s electron is facing is higher in case of C, this C. And since this is sp2 hybridized, so obviously, and both are sp2 hybridized, this C and this C. Now there is a oxygen and here is only carbon. So that's why it is slightly little bit lower binding energy, around 286. Now since this C is sp3 hybridized, so it is the least one, around 280, 284.5 or something. So that is the beauty of the XPS. Very small difference, but you can nicely you can see from the XPS data, and based on that you can check that what are the different uh, nature of that carbon, or whether it is interacting or not, that you can confirm from the XPS. So is it understood here that how the binding energy, or how why it is so much authentic, and how you can get the exact data from XPS, or you can assure that whether it is uh, forming any covalent bond or it is interacting with something or not. You see only 284 to 287, 3 electron volt energy gap, but it is clearly visible. So another important term, that is spin orbital splitting. Yes, yes. Okay, okay, no issue. So what we know from the NMR, that we have learned that whether there is a presence of higher electronegative group, so it is shifting the delta value towards higher ppm, right? Similar, so when there is a presence of electronegative atom, for example, 1 minute. So this carbon C, that is designated by C, it is bonded with two oxygen. Now both this carbon and this carbon, both are sp2 hybridized. Okay, only this carbon is sp3 hybridized, and also this carbon. Now if you check the binding energy, you see that C1s, that A is coming around 284 point something. Okay, and C, that is bonded with the oxygen, it is coming around 289. And this B, since it is also bonded with this oxygen, that's why it is coming around 286. Now why this is? Because whenever there is a electronegative atom, so it is trying to attract that electron of this carbon atom cell. From valence shell electron, it is trying to attract. So whenever this is attracting, so the effective nuclear charge on the 1s will be higher. For example, what we have learned during our 11th or 12th standard, say sodium and sodium plus. So in case of sodium, if there is total 11 number of proton and 11 number of electron, right? So for one electron, one proton is available. Now when it is NO plus, that means you are taking one electron. Now there is remaining only 10 electron, right? Now for that 10 electron, there is 11 number of proton. So obviously there is much more. Now it should feel higher electrostatic interaction. Is it clear right now, till now, that when I am going from Na to Na plus, that now that total 11 proton is attracting 10 electron, but before that it was 11 proton and 11 electron. So similarly, when there is a presence of electronegative atom, here it is oxygen, so it is attracting the electron. So now it is feeling greater effective nuclear charge. So that's why the binding energy, sorry, that's why it is showing that binding energy, it is around this type of C carbon is around coming at 280, 289 most probably, because of the presence of oxygen. So whenever there is a presence of electronegative group, the binding energy will be higher. That is as simple as it is. Now since there is one oxygen, so that's why it is coming around 286, but since there is all are carbon, it is bonded to all carbon, that's why it is coming around 284. Is it clear that why binding energy increased? Okay. So after getting the data, you have to fit it, and the intensity, and how intensity actually different, that is determined by a equation, that is 2j plus 1. For example, if the titanium 2p peaks you consider, the ratio of the heights should be 2:1 for the Ti 2p 3/2. So there is 1/2 and 3/2. So and Ti 2p 3/2 and Ti 2p 1/2 peaks respectively. So if you check 2j plus 1, so that is 2 into 3/2 plus 1, and for 2p 1/2, that will be 2 into 1/2 plus 1. So that is 4:2. That means 1:2 ratio. Similarly, if you consider the 3D 3 by 2 and 3D 5 by 2, you will get the ratio intensity ratio will be 2 is to 3, and similar so for 4F it will be 3 is to 4, just by checking the 2J plus 1. Now, change in binding energy of a core electron of an element due to change in the chemical bonding of that element. And core binding energy are determined by the electrostatic interaction between it and the nucleus. So just you focus that how the electrostatic interaction changes whenever there is a different electronic environment. Based on that, you just imagine that how nucleus is attracting the rest of electron. If there is a presence of electronegative atom, so it is trying to take electron, so there is the chance of higher effective nuclear charge is experiencing. The rest electron will experience higher effective nuclear charge. So that's why the binding energy will increase. So that's why withdrawal of valence electron charge increase the binding energy. So that's why whenever there is a oxidation takes place, so you will get at a higher binding energy peak. And when there is a reduction or addition of valence electron charge, there is a decrease in the binding energy. So this is the depth profiling from the XPS. You can also check the depth profile by bombarding with argon at a uh, different depth, or just by sputtering with energetic air plus to remove the surface atoms by sputtering. Sputtering a sample surface can remove impurities, depends on the sputtering rate, and also angle reduce of XPS. So that in that case you just tilt the sample at a specific angle, that is reducing the takeoff angle, and the photoelectrons collected in the plane of the analyzer have to travel a greater distance. So this is X-ray coming, and here photoelectron is going. Now if you tilt it, now it is covering a little bit. The depth from which the photoelectron are directed without undergoing inelastic collision decreases with the theta value. So just by tilting the substrate, you can get the emission of electron from different depth, and you will get a depth profile of your sample. So is it okay till now, or XRF we can discuss in the next week? I think for today it is okay. We will discuss the XRF next Saturday. Now to you it is clear now how the binding energy change if I change the oxidation state, or if I change the electronic environment surrounding a specific atom. If you have any doubt, you may ask me. Just imagine that what we have learned during the NMR, that how delta value increased with the when it is bonded with a higher electronegative atom. Similar, so here the binding energy will increase. So thank you. So again we will meet next Saturday, and next week we will discuss the XRF. हाँ